Limits and continuity. A function is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. Built into this definition are three things. F of a is defined. The limit as x approaches a of f of x exists. And those two things are equal. A function that's not continuous at a is called discontinuous at a. So here's an example with a graph. We want to figure out where this is discontinuous. At x equals 0, we've already seen that the limit does not exist. So the limit as x approaches 0 from the left is equal to -1. The limit as x approaches 0 from the right is equal to +3. Because those two limits don't match, the limit does not exist. Now at x equals 1, the limit does exist. The limit as x approaches 1 of f of x is equal to 1, since both the left and right limits are equal to 1. However, the function value at x equals 1 is f of 1, which is 2. And so because that dot isn't inside that circle, we have a discontinuity. We want to talk a little bit about the difference between a singularity and a discontinuity. If f of a is not defined, but f of x is defined for at least some values of x arbitrarily close to and on both sides of a, we will say that f has a singularity at a, or that a is a singular point of f. So these diagrams, you see two very similar functions. The one on the left, we have open dots at x equals 2. On the right, we have one open dot and one closed dot at x equals 2. So because f of 2 doesn't exist in the graph on the left, but values of f of x exist very close to 2 and on both sides of 2, we call that a singularity at 2. On the right, f of 2 is defined, it's 1. So because f of 2 is defined, but it's not equal to its limit, then we say that f has a discontinuity at 2. So on the left graph, because it's a singular point at 2, 2 is not in the domain, and so the graph of f is continuous on its domain. On the right, because there's a discontinuity at 2, we say that f is discontinuous at 2. Here's another example. The graph on the left contains a singularity at 0. And so we call y equals f of x in this case on the left continuous on its domain with a singularity at 0. The graph on the right is defined at 0. F of 0 is equal to 0. And so there's a discontinuity in the graph on the right, and so it's not continuous on its domain. Limits and continuity from an algebraic viewpoint. Functions that can be written as a sum or difference of constants, powers of x, exponential functions, radicals, logarithms, absolute values, or trigonometric functions are called closed-form functions. Here's some examples. 3x squared minus absolute value x plus log x. Or maybe root of x squared minus 1 divided by 6x minus 1. Or perhaps e to the power of 3x squared minus 1 over x. functions like piecewise functions are not closed forms. It turns out that every closed form function is continuous on its domain. Thus, if f is a closed form function and f of a is defined, then the limit as x approaches a of f of x exists and is equal to f of a. In order to see some examples of this theorem in action, let's evaluate the limit as x goes to 1 of x cubed minus 8 over x minus 2. First, we note that the function is closed form. We also notice that x equals 1 is in the domain of the function. And as a result, we can substitute x equals 1 in directly. So the limit as x approaches 1 of x cubed minus 8 over x minus 2 is the same as 1 cubed minus 8 over 1 minus 2, or 7. Now, if f of x and g of x are two functions, and they're equal for all x except possibly at a, then their limiting values have to be the same. So the limit as x approaches a of f of x has to equal the limit as x approaches a of g of x. Now, if we look at x squared minus 1 over x minus 1, we can factor the numerator, cancel x minus 1 top and bottom, and see that except at the point x equals 1, x squared minus 1 over x minus 1 is equal to x plus 1. So taking advantage of that, the limit as x approaches 1 of x squared minus 1 over x minus 1 is going to be the same as the limit as x approaches 1 of x minus 1 times x plus 1 over x minus 1, which we know is the same as the limit as x approaches 1 of x plus 1. Since 1 is in the domain of x plus 1, that limit is 1 plus 1, or 2. Here's two piecewise functions, f of x and g of x. We'd like to determine if they're continuous on their domain. So f of x is x squared plus 2 if x is less than 1, and it's 2x minus 1 if x is greater or equal to 1. So f is closed except at x equals 1. At x equals 1, the limit as x approaches 1 from the right of f of x is the limit as x approaches 1 from the right of 2x minus 1, which is 1. And the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the left of x squared plus 2, which is 3. Now, since those limits are different, the limit here doesn't exist, and so f is not continuous. F is going to jump at x equals 1. For g of x, we can see that it's closed form except at x equals 0 and x equals 1. Let's start at x equals 0. The limit as x approaches 0 from the right of g of x is equal to the limit as x approaches 0 from the right of 1 minus x, which is equal to 1. The limit as x approaches 0 from the left of g of x is equal to the limit as x approaches 0 from the left of x squared minus x minus 1, which is equal to 1. And so these limits are the same, and g of 0 is equal to 1, so g has got to be continuous at x equals 1. How about x equals 0? At x equals 1, The function is not defined. So g has a singularity at 1. So therefore, g of x is continuous at all real numbers x except for the singular point x equals 1, which is not in its domain. And so we say that g of x is continuous on its domain. Algebraically, to deal with a limit at infinity, we look at the highest power of x in the numerator and denominator. So for example, if we want to evaluate the limit as x goes to infinity of 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1, we want to divide the top and the bottom by the highest power of x in the denominator. In this case, that's x squared. So we take our limit and we divide both the top and the bottom of our fraction by x squared. We then go ahead and simplify. This gives us the limit as x goes to infinity of 3 minus 1 over x minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. As x goes to infinity, all the terms that are being divided by a power of x are going to go to 0. And so we end up with 3/5. Another example, we want to evaluate the limit as x goes to infinity of negative x cubed minus 4x over 2x squared minus 1. Again, if we think back to the previous example, all we have to look at is the highest power of x in the numerator and denominator. All of the other powers become irrelevant. And so when we simplify this, we can essentially go from the limit as x goes to infinity of negative x cubed minus 4x over 2x squared minus 1 to the limit as x goes to infinity of negative x cubed over 2x squared, because the lower order terms are going to drop out. Here's another example. We want to evaluate the limit as x goes to infinity of 2x squared minus 4x divided by 5x cubed minus 3x plus 5. Again, we're going to start by dividing by the highest power of x in the denominator. If you divide by x cubed, top and bottom, your 4x in the numerator, your 3x in the denominator, and your 5 in the denominator are going to drop out. So the limit as x goes to infinity of 2x squared minus 4x divided by 5x cubed minus 3x plus 5 is equal to the limit as x goes to infinity of 2x squared divided by 5x cubed, which is the limit as x goes to infinity of 2 divided by 5x, or 0 as x goes to infinity.